Hello. Today we're going to cover section 6.2, which is differential equations dealing with growth and decay. The objectives of this section are to use a method called separation of variables, and then we're also going to look at exponential functions, specifically the growth and decay. The first thing we're going to look at are differential equations. So far, we have learned only how to solve two types of differential equations. Right now, we're going to go in and we're going to look at this method that they call separation of variables. And the goal for separation of variables is to rewrite each equation so that each variable, in most cases x or y, are going to occur only on one side of the equation. And we're going to start off by looking at example 1. Example 1, says to solve the differential equation given y prime is equal to the square root of x divided by 7y. Now, the first thing we want to do is we want to rewrite our equation so that all of the y pieces occur on one side and all of the x pieces occur on the other. So to do that, I'm going to multiply by this 7y so that I can cancel that out of the denominator. When I do that, I get 7y times y prime is equal to the square root of x. Now, to get rid of my y prime, I'm going to go and I'm going to integrate each side. So I'm going to come in here and integrate. And when I integrate 7y times y prime, I'm going to get 7 over 2 y squared equals, now remember the square root of x is really x to the 1/2. So to integrate that, I'm going to add 1 to my exponent to give me 3/2, and then I have to multiply that by the reciprocal, so I'm going to end up with 2/3 x to the 1/2. I'm sorry, 3/2. Let me erase that out here. So 2/3 x to the 3/2 plus c. Now, the thing with solving a differential equation is we want to clear out any denominators that we have, and we want to isolate the variable c. So to do that, I'm going to first go ahead and isolate c. So I get c is equal to 7/2 y squared minus 2/3 x to the 3/2. Then, in order to clear up my denominators, I see that I have a common denominator of 6. So if I multiply everything by 6, I'm going to be able to cancel out that denominator, and I'm going to end up with 21y squared minus 4x to the 3/2. And all of this is equal to c. Now, I know at the beginning of the year when we went over problems dealing with y prime and dy dx, some of you prefer the dy dx, and that's fine too. If we want to do that, let me change my pen color here. We can actually rewrite all of this in terms of dy dx. So I could have taken my original equation, and I'm just going to do all of this on the side here, and I could have written this as dy dx is equal to the square root of x over 7y. Now, as with any other differential equation, I'm going to separate my variables, and I'm going to get the y's and dy's on one side and the x's and dx's on the other. So to do that, I'm going to end up with 7y dy is equal to the square root of x times dx. And then I'm going to go ahead and integrate just like I did before. So when I integrate both sides, I can see that when I integrate 7y dy, I still end up with my 7/2 y squared is equal to my 2/3 x to the 3/2 plus c. And I'm going to go through and clear out my denominators, get all of my or I'm going to set the equation equal, or C equal to the rest of my stuff. So I still end up with C equals 21y squared minus 4x to the 3/2. The next thing we're going to look at are growth and decay models. The growth and decay models, I know you guys have had a lot of exposure to this between your science classes and your math classes, but in calc, we're going to think of growth and decay models as the rate of change in y, or the dy dt, is being proportional to y. So we're going to get the equation dy dt equals ky. And in your book, you'll see that you have Theorem 6.1, which is talking about the exponential growth and decay model. And what it tells you, it says, if y is a differential function such that y is greater than 0 and the derivative is equal to ky, for some constant k, you get this equation y equals c times e raised to the power of kt. Now c is going to be like our initial value. K, if you think back to Algebra 1 and Algebra 2, is still a proportionality constant. And then if you think back again to like Algebra 2, we know that if our K value is positive or greater than 0, then we have a growth situation. If it's less than 0, then we have a decay. So this leads us into example 2, and it says the rate of change of y is proportional to y when t equals 0 and y equals 250, and when t equals 1 and y equals 400. What is the value of y when t equals 4? What we're going to do is we're going to start out with the fact that y prime equals ky, and we know that y and t are related by the equation y equals c times e to the kt. So because we know these two equations, we can actually go in and find the value of c, which is our initial value, and our value of k by using the initial conditions that were given. And the first initial condition we're going to use is this t equals 0 and y equals 250. So if I go and I plug those into my y equals c e to the kt equation, I end up with 250 equals c times e. I still don't know what k is, but I know that t is equal to 0. Well, when I have a value of, or e, or and in this case, any number raised to a power of 0, because k times 0 is going to give me 0, I know that this whole thing is going to become 1. So I really have 250 equals c times 1, or c is equal to 1. With that information, I'm going to go in and go back and use my other condition that they gave me, which was t equals 1 when y equals 400. And I'm also going to use this value of c, I apologize, c is actually equal to 250. So I'm going to use t equals 1, y equals 400, and c equals 250. And I'm going to plug all those back into this y equals c e to the kt equation. So I end up with y as 400 equals my new c value, which is 250, e. I still don't know what k is, but I do know that t is equal to 1. So now I have 400 equals 250 times e to the power of k. And like we would with any other algebraic equation, if we want to isolate the variable, the first thing we need to do is get rid of everything else. So I'm going to divide 400 by 250, and when I simplify that fraction, I end up with 8/5 equals e to the k. Now if I want to isolate my k value, all I'm going to do to undo the e is I'm going to take the natural log of both sides, and I end up with the natural log of 8/5 equals k. Now this is where I would highly suggest that you, once you enter this into your calculator, that you use the storing feature. In my case, I stored it and I called it variable a. You can call it whatever you want to, but K is approximately equal to 0.47 once you store this. So now that I know what K is, I can go back into my original, I can go back into my original function and say that y is equal to 250, which is my calculated C value, e to my K value, which is really the natural log of 8/5 times my T value. Now, my problem said, what is the value of y when T equals 4? So what I'm going to do is I'm going to go in and I'm going to plug a 4 in for this T and solve my equations. This is where it comes in handy to use that stored value for your natural log of 8/5. When I plug all of this into my calculator, I end up with y equals 1,638.4. Another typical problem that you'll run into with your exponential growth and decay problems is dealing with half-life. The half-life is the number of years that's required for 1/2 of the atoms in a sample of some type of radioactive material to decay. So if we look at an example dealing with this, my problem says a sample contains 1 gram of radium. Will more than 1/2 gram of radium remain after 1,000 years? And the problem gives us that the half-life of radium is equal to 1,599 years. Now to do this, I'm still going to use that equation y equals CE to the KT, and I'm going to use the information that they gave me. They told me that y equals 1 gram when my initial time was 0. So using that, I'm going to plug in 1 gram equals, I still don't know what C is, but I know that E is raised to the power of K, which I still don't know, times T, which is 0. And again, I'm going to see that E raised to the K times 0, or E to the 0, all of this is 1. So I end up with C is equal to 1. Now with that, I'm going to go back and plug that into my original equation. So now I have y equals, I apologize, C is actually equal to 1 times E to the KT. I also know, based on the information that was given to me up here, that after 1,599 years, I will have half of my sample left. So I can actually use that information and say that T is equal to 1,599 when y is equal to 0.5. So with that, I can take my new C value that I have, and I can plug in 0.5 is equal to my value of C, which is 1, times E to the K, times T, which is 1,599. And again, I'm going to divide, in this case, when I divide by 1, I'm still going to have 0.5. So if I have 0.5 equals E to the 1,599 K, I need to solve for that constant K. And to do that, I'm going to take the natural log of both sides. So I end up with a natural log of 0.5, or 1/2, is equal to 1,599 K. If I go through and divide everything by 1,599, I end up with K is equal to the natural log of 1/2 divided by 1,599. Again, this is an excellent place to use the storing feature on your calculator to store that value so you don't have to retype all of this in later. Because now that I have that, now I'm going to go in, I have K, I have my C, I know that I'm trying to find out how many grams I'm going to have after 1,000 years. So all I have to do is plug in all of the pieces that I know. So I have y equals 1 times e to the value of k, which in this case is the natural log of 1/2, divided by 1,599, and I'm going to multiply that value, in this case, by 1,000 years. When I type that into my calculator, I got 0.648 grams. And the original question says, will more than 1/2 gram of radium remain after 1,000 years? And because 6.48 is greater than 0.5, we will say yes. Okay, in the previous few examples, we didn't actually have to solve a differential equation in the form of y prime equals ky. Now, in the next problem that deals with Newton's law of cooling, we're going to have to use the separation of variables technique that we covered within the first few examples. Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So when we look at example 6, it says let y represent the temperature measured in degrees Celsius of running water that's kept at 18 degrees Celsius. So that's the water temp. If a hard-boiled egg, which is boiled at 98 degrees Celsius, is placed into that running water, the temperature of the hard-boiled egg after 5 minutes is 38 degrees Celsius. How much longer will it take that egg to reach a temperature of 20 degrees, and that should be 20 degrees Celsius, I apologize. So we'll say degrees Celsius. Okay, so the first thing we're going to have to look at is the rate of change is the difference between our y and our 18 degrees. So I know that y prime is equal to my constant times y minus my 18 degrees. So as I would with any other differential equation, I'm going to go ahead and solve that. And I'm actually going to turn my my y prime into a dy dt. And this is going to equal k times y minus 18. And as we did earlier with our differential equations, we're going to separate our variables, all of the y pieces on one side, all of the dt pieces on the other. So I end up with 1 divided by y minus 18 times dy is equal to k times dt. So now I'm going to go through, in order to solve this, I'm going to integrate both sides. And when I integrate, what I'm going to do here is I see that I really have u equal to y minus 18. So I'm going to say du is equal to 1 dy. And I see that I have the situation of 1 over u times du equals the integral of k dt. So when I integrate 1 over u, I know that that's going to give me the natural log. And if I plug in my u stuff, I have the natural log of the absolute value of y minus 18. And when I integrate k with respect to t, I'm going to end up with kt plus c. So now, using the initial conditions that I was given, I'm going to have to go back and use that equation that y equals c e to the kt so that I can use those initial conditions. So I end up with y minus 18 is equal to ce to the kt plus c. Oops, I'm sorry, that plus c goes in the top. So ce times kt plus c, all of that's in the exponent there. So when I go through and I simplify, I really end up with y equal to ce to the kt plus 18. And now I can go ahead and use those initial conditions. And if you recall back, we were given that y equals 0, or I'm sorry, t equals 0. So at time 0, that temperature was 98 degrees of that egg. So 98 degrees Celsius. So if I plug those in, I end up with 98 is equal to C E to the K times 0 plus 18. If I subtract 18 from both sides, I have 80 equals C E raised to the power of 0, which we know that this is going to go to 1. So I have 80 equals C. And when I go and I plug that back in, I now have y equals 80e to the kt. Okay, and I'm going to use the other condition that was given to me, and that was when t was equal to 5 minutes, I know that y equaled 38 degrees Celsius. So again, I'm going to go through and plug in everything I know so that I can go and solve for my k value. So I have, 38 is equal to 80 e to the k times 5. I'm going to divide both sides by 80. So I end up with, I'm sorry, and I still have my plus 18 out here. I did drop that. I apologize. So I'm going to go 38 minus 18, which gives me my 20, equals 80e to the 5k. I'll now go through and divide by 80. So 20 divided by 80 is 1/4 equals e to the 5k. And now I'm going to take the natural log of both sides. So I have the natural log of 1/4 is equal to 5k. Now I'm going to divide by 5. So I have k is equal to the natural log of 1/4 divided by 5. Again, store this in your calculator. Okay, so now that I have that, I can plug this in and solve for my time t. So to do that, I know that my goal is I wanted to know what my temperature, or how long it was going to take me. So what was the time it was going to take me to reach a temperature of 20 degrees? So now I'm going to plug my temperature of 20 degrees Celsius in for my y value and set that equal to my 18 plus my c value of 80 e. I now know that k is going to equal, this is why we store this, the natural log of 1/4 divided by 5 times t. So to solve now, I'm going to go ahead and subtract the 18. So I get 2 is equal to 80 e to that stored feature in your, or stored number in your calculator times t. When I divide by 80, I end up with 1/40 is equal to e times their stored function there times t. I'm now going to take the natural log of both sides. So the natural log of 1/40 equals e, we're going to get rid of that e when we take the natural log of it. So that equals the natural log of 1/4 over 5, or that stored number, times t. Then I'm going to divide by this stuff. So I get the natural log of 1/40 divided by the natural log of 1/4 divided by 5. And this is going to give me t, And from my calculations, I have t is approximately equal to 13.3 minutes.